Alright, so to start this problem, we have the system here where there are two boxes. One's on an incline like this, and the other is hanging, connected via this frictionless pulley. So the first thing I'm going to do, of course, is draw my free body diagram. So thinking about that 40 kilogram box on the incline, it has the force of gravity acting down on it. There's going to be the force of tension from the rope, and then, of course, the normal force from the incline itself. Alright. And then moving on to the 15 kilogram, we're going to have a force of gravity on that as well. We're going to have tension holding that up. No normal force because it's not on a surface. And those are actually the only two forces on that box. The one thing I'm going to do is I'm going to call this FG1 and that FG2. They are two different forces of gravity because they're two different masses. So we should call them two different things. Now it's okay to call these FTs the same thing though because they are the same force. I'm going to go ahead now and break that force of gravity into my x and y components. So there's my y, there's my x. So the y will be Fg cosine of theta, and the x will be Fg sine theta, and both those are Fg1. Okay. Now that I have that, I'm going to go ahead and set up my max and my may for each one of the boxes. Okay, I really only care about the x direction here, so that's the only one I'm going to set up. I could set up my y, but there's no friction, and I'm really just worried about it not moving up or down the incline, so that's purely an x thing in this situation. So if I think about for the box on the incline, the sum of the forces in the x is equal to max. So I'm going to have Fg1 sine of theta minus Ft, and I'm told the system is going to remain stationary, and so that means that this entire side here actually is 0. So given that, I can sub in for the force of gravity, of course, is mg, and so I can say m1g sine of theta is going to be equal to ft. So that's one equation that we have here. I'm going to go ahead and set up my other equation. For that one, we're worried about y forces because that's all vertical stuff. So sum of the forces in the y equals may. This one is also at rest. It's connected, so I can say my acceleration is 0 here too. And so it's going to be ft minus fg2 now equals 0. And so rearranging and simplifying this, I can say that ft will be equal to m2g. So what I can do now is I can take these two equations that I just came up with, and I'm just going to go ahead and set them equal to each other. I see that both equations are equal to ft, so I'm just going to set the equations then equal to each other. So we can say m1g times sine of theta is equal to m2g. We could go ahead and cross off the g's, or you can just sub in what you know. We know mass 1 is 40. We, of course, know g is 9.8 times sine of theta is going to be equal to 15 times 9.8. So we end up with 392 sine of theta equals 147. I'm going to divide by 392 and take the inverse sine. So theta is going to be the inverse sine here of 147 over 392. So I end up with an angle here where they will remain stationary of 22 degrees. All right, so that wraps up part A. Part B, we're going to look at what the acceleration would be if the angle is 30. All right, so for the second part, we're saying our angle is now set to 30 degrees. Given that it stayed at rest at 22 degrees, if we up it to 30, that means that this box is going to accelerate down the ramp, and therefore the other box will accelerate up in the vertical direction. So I'm going to redo my F equals ma, and I don't need to fully redo it. It's still Fg1 sine theta minus Ft for the box on the incline, but now there is an acceleration. So I'm going to say it's equal to m1a. Again, calling that 40 box m1. I can sub in what I know here, so I can say m1g times sine of theta minus ft is going to be m1a. I'll worry about the actual numbers in a second here. For the other one, again, same basic equation here. The only thing we're going to have different is we are going to have an acceleration. So I'll say Ft minus Fg2 equals m2a. So Ft minus m2g equals m2a. I'm going to take that equation and add it to this equation here. And so we see here that those FTs cancel out, and what we end up getting here is m1g sine theta minus m2g equals the total mass of the system, m1 plus m2 times a. And that makes sense because this force here, that m1g sine theta, is really the force driving it down the ramp. This m2g is holding it back, and we end up with the total mass of the system. So now I'm going to plug in the things that we know here. So it's going to be 40 times 9.8 times sine of 30 minus 15 times 9.8 is going to be equal to the total mass, which is 55, times a. This all becomes 49, so 49 equals 55a, and that means that our acceleration is 0.89 meters per second squared. All right, moving on to this next problem, we have these two boxes being pushed across a frictionless floor here with some force F. We know the masses are m and 3m, and we want to figure out the acceleration. So this is all algebraic here, but we want to figure out the acceleration based off of this F here. So what I'm going to do for this one's a great case for one to do as a system. So I'm going to treat those two boxes as a single system, and then the forces I have are F. Of course, I have a normal force going up and a force of gravity going down. So just thinking about the forces in the x direction, the only x force I really have is that F, so I can just say F is equal to the mass of the system, which is 4m times a, and so my acceleration here is just going to be F over 4m. All right. The next question then asks, how much force does a smaller box exert on the bigger box? And so now I'm going to think just about the forces acting on the bigger box here. And so we have 3m. What forces are acting on that? Well, of course, we have our normal force. We have the force of gravity. And then I'm going to just call this F1, we'll say. And that's going to be the force from that smaller box on the bigger box. And so if I set up my F equals ma once again here, in the x direction, of course, we have F1 equals 3m times a. I can sub in that acceleration that I just found, which was F over 4m, and I find that F1 here is just going to be equal to 3/4 of the full thing, which makes sense, okay? The whole system is a mass of 4m, and it needs a force of F to accelerate it, so one that has a mass of 3m, 3/4 the mass, should require 3/4 the force. So for this final question here, I'm asked if the position of the boxes is switched. So we now have the 3m box here on the left-hand side, and then the smaller box of m on the right, still pushing with a force of F here. We want to know how the force between the two boxes changes. Does that force increase, decrease, or remain the same? And the answer here is going to be that that force will decrease. Okay, and really what I would think about is I would think solely about the forces that we have on the 3m, which is the box on the right, and originally, compared to the forces we have on the m, the new box. Okay, so if we just think about this new situation where m is on the right, and there's some force, we'll call it F2, being used to accelerate it, that is the force between the two boxes. That F2 is going to be smaller than this F1, because in this original case, F1 was accelerating the 3m box. It was accelerating more mass. Okay. Now F2 is accelerating just the m box, so it's not accelerating as much mass. The acceleration is the same in both cases because the overall force on the system and the overall mass of the system is the same, but now that force between them has to accelerate less mass, and therefore the force between them will decrease. All right, one more problem here. So we have two boxes that are hooked up to this system here. This is referred to as an Atwood machine. Box 1 here, box 2 here, they're connected via ropes over frictionless, massless ideal pulleys. So we first want to think about what forces are acting on these objects. We want to be very specific here and draw the forces relative to the other forces. So we want to draw them to scale. So both boxes, I'm going to start with this, both boxes have a tension force acting on them, and those tension forces are going to be the same. So I'm going to say the tension forces are just 2 bars high here, because I know that the tension acting on each one is going to be the same. The other thing I'm going to think about is I do know that box 2 has more mass, so this system is going to accelerate up like that, and then box 2 is going to accelerate down. So when I think about my forces of gravity, I need to make sure that that shows that acceleration. So for box 1, I'm just going to say the force of gravity is just 1 bar there. I'll call it FG1. For box 2, I'm going to say it's 3 bars. And the reason I'm doing that is now, okay, box 1 has more force up, so it will accelerate up. Box 2 has more force down, so it will accelerate down, and that matches what we know about the two boxes. Next thing I'm going to do is I'm going to set up my F equals MA for each one. Starting in the y direction, and this is going to allow me to derive an expression for that acceleration. So for block 1, which is accelerating up, I'm going to say that Ft is the positive direction, so Ft minus Fg1 equals M1A. So I can say Ft minus M1G equals M1A. So that's one equation I have. For the other box, I can say Fg2 minus Ft, and the reason I'm doing that is because this one is accelerating down, is equal to M2A, so M2G minus Ft equals M2A. So I'm going to take those two equations and we're going to add them together and ultimately solve for my acceleration. Alright, so here I have my forces, and my two force equations lined up. I see, of course, that tension is going to go away here, so what I'm left with is M2G minus M1G is equal to M1 plus M2, the sum of those masses, times A. That makes sense. Those force between them goes away, and I'm left with the total mass of the system. Solving for A here, I'm just going to put it over M1 plus M2, so I'm going to be left with M2G minus M1G over M1 plus M2. That's going to be equal to my acceleration. Some people will factor out the G that we have here in both terms up top. And so what that ends up looking like is it really ends up being G times M2 minus M1 over M1 plus M2. Is going to be equal to my acceleration. So either expression is valid. It's really just a style choice at that point. Alright, so for this last part we have a new situation. We've added in block 3 here. Okay, so I'm going to once again think about the forces acting on this system. So I have F1G and a tension force here. And I have F2G, or Fg2, and a tension force here as well. Okay. The one thing that changes though is now these are two different ropes. All right, and so that means that my tension forces are not going to be the same for both of them. So I'm going to call this Ft1, that Ft2. Block 3, of course, has a normal force, the force of gravity, which we'll call Fg3, and then it's going to have Ft2 and Ft1. So we want to know what is going to happen to the acceleration of our system. Will it be smaller, larger, or the same as in our original two-block system? And the key thing to really think about here is actually not all of these forces, but rather thinking about this kind of like a system. So we have our block M1 here, connected by rope to block M3, connected by rope to block m2. And if we think about the forces that really are responsible for accelerating the system, all right, it's not any of the FTs. They just hold our system together. And really, if we think about FG and FN on block 3, they're not accelerating the system because those two forces balance out. The only things accelerating the system are F1G and F2G. F1G, of course, is going opposite the direction of the acceleration. Okay. F2G is the thing that ultimately is causing it to accelerate. So this is the same set of forces that we had in our original situation. Okay, we still had F2G and we still had F1G. The only thing that has changed for our system is the total mass. And because we now have more total mass but the same net force, the system will have a lower acceleration. Okay, so ultimately it's just going to be a smaller acceleration because the forces on the system have not changed, the outside forces. However, the total mass of the system has changed.